press your hand flat against the table and push. It pushes back solid and sure, and that solidity feels like the simplest fact in the world. Almost all of the weight behind that push comes not from the tiny particles inside the table, but from the energy of a force holding them together, and the lightest messenger of that force is a particle called the pion. The pion is what this whole story is about. It is the smallest piece of the strong nuclear force, the thing Hideki Yukawa imagined in 1935 to explain why the nucleus does not fly apart. We will build up to it slowly, one simple step at a time, starting from a question a child could ask. What holds the centre of an atom together? If you enjoy this kind of slow look at the world, take a moment to subscribe and we will begin. Hold a stone in your hand and feel how complete it is. It has edges, weight, a surface that stops your fingers from passing through. Nothing about it suggests that it is mostly empty. Yet if you could shrink down and walk into the stone, past the smooth face of it and into a single atom, you would find almost nothing there. An atom is a vast, quiet hall. At its very centre sits a speck so small that, if the whole atom were the size of a sports stadium, that speck would be a grain of rice resting on the centre line. Everything else is the thin haze of electrons spread out in a cloud, and between them and the centre there is only distance. That tiny speck at the heart is the nucleus, and almost all of the weight of the stone lives there. The electrons are light, barely a scrap of the total. Strip them away and the mass hardly changes. So the heaviness you feel in your palm, the solid pull of the stone toward the ground, comes from those grains of rice scattered through the empty halls of countless atoms. The solidity is mostly empty space held in a particular shape. That alone is strange enough to sit with for a moment. The world feels full, and it is mostly room. But the deeper question lives inside that grain of rice at the centre. The nucleus is not a single smooth thing. It is built from smaller pieces packed in tight, and those pieces carry a problem with them, a problem that should tear the centre of every atom apart before it ever forms. To see the problem, you have to know what the pieces are. The nucleus is made of two kinds of particle, and physicists call them protons and neutrons. A proton carries a positive electric charge. A neutron carries no charge at all. It is electrically blank, which is where its name comes from. In the simplest atom, hydrogen, the nucleus is a single lonely proton. In the iron at the core of the stone, dozens of protons and neutrons are crowded together into that one tiny speck. And here is where the trouble starts. You already know from magnets and from the shock of static on a dry day that like charges push each other away. Two positive charges shove each other apart, and the closer you bring them, the harder they shove. Inside the nucleus, protons sit packed against protons, all of them positive, all of them crammed into a space smaller than anything your eye could ever resolve. The push between them there is not gentle, it is ferocious. By every rule of electricity you have ever felt, that nucleus should explode in an instant, flinging its protons in all directions. It does not. The iron in the stone has held its centre together quietly for billions of years, since before the Earth had a surface, since the atoms were forged in a dying star. Something at the centre is stronger than the fierce electric push, strong enough to overpower it completely and hold the protons in place against their own desire to fly apart. Something is gripping the heart of the atom and refusing to let go. That something is the real subject of this story. It is a force, and it is the strongest force in nature, stronger than gravity and electricity by amounts that are hard to picture. For now, hold just the question, plain and simple. What holds the centre of an atom together? The stone in your hand is solid because that grip never fails. Everything that follows is the slow unfolding of what that grip is, where it comes from, and the small, fleeting particle that turned out to carry it. We begin where the trouble is worst, in the crowded centre itself, where the protons are pressed together and electricity is screaming for them to part. Picture the nucleus of an iron atom up close, swollen in your mind until you can see its parts. It is not a smooth ball. It is a cluster of separate pieces, 26 protons and 30 neutrons in the most common kind, packed against one another like fruit pressed into a jar with no room to spare. Each piece is a tiny sphere, and they touch, and they are held in a clump barely a few times wider than a single one of them. There is no empty hall here, the way there was in the atom as a whole. The nucleus is the one crowded room at the centre of all that emptiness. That crowding is the whole problem. Out in the wider atom, the electrons keep their distance, spread thin and far apart. In the nucleus, the protons have nowhere to go. They sit shoulder to shoulder, and every one of them carries the same positive charge, and the electric force between charges grows stronger the closer they come. Halve the distance between two protons, and the push between them grows 4 times as fierce. In the nucleus, that distance is as small as it ever gets in ordinary matter, so the push is enormous. Put a number on it, just to feel the scale. The electric repulsion between two protons touching inside a nucleus is roughly the weight of a small coin pressing down, all of it concentrated on a single proton lighter than anything you could ever weigh on a scale. That does not sound like much until you remember how little a proton is. For a thing that small, that force is a hurricane. Left alone, it would blow the nucleus apart in far less than the blink of an eye, in a time so short there is no everyday word for it. So the question from before sharpens. It is not just that something holds the nucleus together. Something holds it together while fighting against one of the strongest pushes in the everyday world, and wins every time in every atom, for ages without end. Whatever does the holding has to be stronger than electricity at these tiny distances, and not by a little. There is another clue hidden in the neutrons. Notice that the nucleus is not all protons. It carries neutrons too, and the heavier the nucleus, the more neutrons it needs. Iron has more neutrons than protons. Lead has half again as many. The neutrons carry no charge, so they feel none of the electric push and add none of it. They are not there to make the crowding worse. They are there in part to help hold the whole thing together, adding their share of the grip without adding to the repulsion. A nucleus of pure protons with no neutrons to dilute the charge falls apart almost at once. Only the lightest nuclei manage with protons close to even, and even they lean on neutrons as they grow. That tells you something about the holding force already. It does not care about the electric charge the way electricity does. A proton and a neutron, one charged and one blank, are held together just as firmly as two protons, perhaps more so. The grip treats them almost as the same kind of thing. Whatever this force is, charge is not what it reaches for. So we have a force at the centre of the atom that is stronger than electricity up close, that pulls protons and neutrons alike, and that has to exist or no nucleus heavier than hydrogen could survive a single instant. Physicists gave it a blunt and honest name. They called it the strong force, because it was simply the strongest thing they knew. Naming it was easy. Understanding its manners, the strange way it behaves at different distances, took far longer, and that is where we turn next. The strong force does not behave like any force you have ever felt with your own hands. Gravity and electricity both reach out across distance, fading slowly as things move apart but never quite letting go. The sun holds the Earth from 93 million miles away. A magnet tugs a nail from across the table. These forces have long arms. The strong force has almost no arm at all. Bring two protons close, and within the cramped space of a nucleus, the strong force grips them hard. Pull them apart even by a tiny amount, even by a few times the width of a proton, and the grip vanishes. It does not fade gently the way gravity fades. It drops to nothing with startling speed, as if switched off. Two protons sitting a short distance outside a nucleus feel no strong pull between them whatsoever. They feel only the electric push, shoving them apart. The strong force lives entirely in close quarters. Step back the smallest step, and for all the world it might not exist. This is why no one felt it for so long, and why it took until the 20th century to even suspect it. Gravity shaped the heavens in plain sight. Electricity sparked and crackled where anyone could see. The strong force hid in a space too small to enter, switched off everywhere except inside the nucleus itself. To reach it, physicists had to go down to that grain of rice at the centre, and they had no tools to go there until they learned to break atoms open. There is a second strange manner, deeper than the first. You might expect that the more particles you cram into a nucleus, the more tightly each one is bound, the way a bigger crowd presses you harder from all sides. That is how electricity works. Every proton pushes on every other proton, so the push piles up faster and faster as the nucleus grows. The strong force does not pile up that way. Each proton or neutron binds only to the few neighbours right beside it, not to every particle in the nucleus at once. It is as if each piece can hold hands only with those touching it, and ignores the rest of the crowd entirely. Physicists call this saturation, and it is a deep clue. A particle deep inside a large nucleus is no more tightly held than a particle inside a small one, because either way it is gripping only its immediate neighbours. The grip fills up, saturates, and takes no more. You can see the same behaviour in a drop of water. A water molecule in the middle of the drop touches only the molecules right around it, not every molecule in the whole drop, and so a large drop and a small drop hold each of their inner molecules with about the same strength. The nucleus binds like a liquid drop, and that picture, the nucleus as a tiny drop of dense fluid, became one of the most useful in all of physics. So the strong force has three odd manners, and they fit together. It is fierce up close, far stronger than electricity. It is gone at any real distance, with no long arm at all, and it saturates, gripping only the nearest neighbours rather than the whole crowd. Any explanation of this force would have to account for all three at once: the strength, the sharp cut-off, and the short reach. In the 1930s, that was a tall order. No known force behaved like this. Electricity and gravity reached out forever. Here was something that reached out barely at all, then stopped. The puzzle sat there, waiting, until a young physicist in Japan looked at that sharp, short reach and saw in it a clue no one else had read. The reach itself, he realised, was telling him something about what carried the force. In 1935, a 28-year-old physicist named Hideki Yukawa was working in Japan, far from the great laboratories of Europe where most of the new physics was being made. He was quiet, often unwell, and worked largely alone, turning over in his mind the puzzle of what held the nucleus together. He had no accelerator to smash atoms, no grand apparatus. He had pencil, paper, and a willingness to take an idea from one part of physics and carry it somewhere it had never been used. The idea he borrowed was about how forces work at all. By the 1930s, physicists had a new way of picturing the electric force. Two electrons do not simply feel each other across empty space in this picture. Instead, they pass something between them. One electron throws out a small packet of light, a particle called a photon, and the other catches it, and in that throwing and catching the force is carried. The photon is the messenger of the electric force. Every push and pull between charges is really a constant invisible game of catch, particles of light flying back and forth too fast and too small to see. Yukawa took that picture and asked a simple question. If the electric force has a messenger particle, might the strong force have one too? Might protons and neutrons hold together by tossing some particle back and forth between them, the way charges toss photons? It was a natural thought once the photon picture existed, but it ran straight into the strange manners of the strong force, and that is where Yukawa's real insight lived. The photon has no weight at all. It is massless, pure energy, and that masslessness is exactly why the electric force has such a long arm. A massless messenger can travel forever, so the force it carries reaches across any distance, fading slowly but never stopping. The strong force does the opposite. It dies at the smallest distance and has no reach at all. If the strong force also worked by a messenger, that messenger could not be like the photon. It could not travel far. It had to be a particle that could only ever cross the tiniest gap before vanishing. Yukawa saw what that meant, and it was the heart of his idea. A messenger that can only cross a tiny gap must be a heavy messenger. A massless particle ranges everywhere. A particle with weight is hemmed in, allowed to exist only for the briefest flicker, and so able to carry the force only the shortest way. The short reach of the strong force was not a flaw to explain away. It was a measurement. It was telling Yukawa directly how heavy the messenger of the strong force had to be. He did the arithmetic. From the known size of a nucleus, the distance over which the strong force had to reach, he worked out the weight his messenger would need. The answer came out to a particle roughly 200 times heavier than an electron, yet still lighter than a proton, sitting in a middle range where no particle had ever been seen. Because its weight fell between the light electron and the heavy proton, the new particle was later called a meson, from a Greek word for middle. In 1935, Yukawa published this, a force carried by a heavy messenger of a definite predicted weight. It was a bold guess from a man with little more than a clear idea, and it was met mostly with silence. No such particle had been found. A prediction of a brand new particle, from a young theorist working far from the centres of physics, was easy to set aside. Yet the logic was tight, and it tied the reach of a force to the weight of a particle in a way that could be checked. All anyone had to do was find the middleweight particle. The hunt would take more than 10 years, and it would pass through one of the most confusing wrong turns in the history of physics. Yukawa's central claim deserves to be slowed down and looked at on its own, because it is the hinge the whole story turns on. He said the reach of a force fixes the weight of its messenger. The shorter the reach, the heavier the messenger. That sounds almost backward at first, so it is worth building the reason from the ground. It rests on one of the strangest rules in physics, a rule about borrowing. In the world of the very small, energy is not perfectly fixed from one instant to the next. For a fleeting moment, a particle can come into being out of nothing, borrowing the energy it needs to exist, as long as it pays that energy back fast enough. The universe permits the loan, but only briefly, and there is a strict relationship between the size of the loan and its length. A small loan can be held for a longer time. A large loan must be repaid almost at once. A messenger particle is exactly this kind of loan. When a proton throws out a messenger to a neighbour, that messenger is borrowed from nothing for an instant, and it must be reabsorbed before the debt comes due. This is why it is called a virtual particle. It lives on borrowed time and cannot be caught in the open. The question is how far it can travel during its short borrowed life, because that distance is the reach of the force. Now bring in the weight. The energy needed to make a particle exist includes the energy locked in its mass, the famous link between mass and energy that says even a particle at rest carries energy simply by weighing something. A heavy messenger is a large loan because its mass alone cost a great deal of borrowed energy. A large loan must be repaid almost instantly, so a heavy messenger lives for the briefest flicker, and in that flicker it can travel only the tiniest distance before it must vanish back into nothing. Its weight chains it to a short range. A light messenger is the opposite. It is a small loan, cheap to bring into being, so it can be held for a longer time and can travel farther before the debt comes due. And a massless messenger, like the photon, is a loan of almost nothing, which can be held without end and can travel without limit. That is why the electric force reaches across the room and across the solar system. Its messenger weighs nothing, so its borrowed life is endless and its reach has no edge. This is the whole engine of Yukawa's idea, and you can run it in either direction. Start with a massless messenger and you get a force with infinite reach, like electricity. Start with a heavy messenger and you get a force that dies at a short distance, like the strong force. Or start, as Yukawa did, with a measured reach, the size of a nucleus, and run the logic backward to find the weight the messenger must have to give exactly that reach. The reach you can measure, the weight falls out of it. When Yukawa ran the numbers, the nucleus told him its messenger weighed a couple hundred times what an electron weighs. He did not pull that figure from a hat. It came from the size of the nucleus through this exact chain of reasoning The borrowing rule turned into a scale. Measure how far the force reaches, and the weight of the carrier is no longer a free guess, it is pinned down. There is a quiet beauty in this that is easy to miss. A force you cannot see, carried by a particle no one had found, was made to give up the weight of that particle through nothing more than the size of the region it acts in. The invisible was forced to declare itself. All that remained was to go out into the world and find a particle of that exact middle weight. And in 1937, two physicists studying the rain of particles from space found one. For a while, it looked like Yukawa had been proven right. Before following the hunt into the sky, it helps to hold in your mind the exact shape of the force Yukawa described, because that shape is what the experiments would have to match. A force is not just strong or weak. It has a profile, a way its strength changes as two particles move apart, and Yukawa's idea gave the strong force a very particular one. Think first about the electric force again, for contrast. Its strength falls off with distance in a slow, graceful way. Double the distance between two charges and the force drops to a quarter. Triple it, and the force drops to a ninth. It fades, but it fades politely, stretching out across great distances with always a little left over. There is no point at which you can say the electric force has truly ended. It just grows ever fainter, on and on. Yukawa's force does something far more abrupt. Up close, inside the tiny range set by the messenger's weight, it is enormously strong, stronger than electricity. But as you move outward, it does not merely fade, it plunges. Past a certain short distance, it falls away so steeply that for all purposes it is simply gone. The strength drops not like a gentle slope but like a cliff. Inside the range, full force. Just outside it, nothing. The reason for the cliff is the borrowed life of the heavy messenger. The messenger can travel only so far before it must vanish, and the chance of it reaching any farther falls off sharply with each extra step. So the force it carries is choked off hard at the edge of that reach. Physicists wrote this shape down in a clean piece of mathematics now called the Yukawa potential, and while the equation itself can stay on the page, its meaning is simple to picture. It is a force with a built-in edge, a wall of strength close in and near silence beyond. That edge is set by a single number, the weight of the messenger. A heavier messenger pulls the edge in tighter, making the force reach even less far. A lighter messenger lets the edge out, giving the force a longer reach. So the shape and the weight are locked together. Tell me how heavy the messenger is, and I can draw you the exact profile of the force, where it is strong and where it dies. Tell me the reach of the force, and I can tell you the messenger's weight. They are two faces of one fact. This shape explained the strange manners from before all at once. The fierce strength up close, the vanishing at any real distance, and even the saturation all came from a force with a sharp, short edge. A particle deep in a nucleus binds only to its nearest neighbours, because the force simply cannot reach past them. The cliff in the force is the reason each piece holds hands only with those right beside it. One idea, a heavy messenger, drew the whole odd profile in a single stroke, and the shape made a promise that could be tested. If the strong force really had this profile, with this particular edge, then its messenger had to weigh a particular amount. The couple hundred electron masses Yukawa had calculated. Find a particle of that weight, show that it interacts strongly with nuclei, and the picture would be complete. Fail to find it, or find that the particle of that weight ignored nuclei entirely, and the whole idea would be in trouble. So the search had a clear target. Not just any new particle, but one of middle weight that gripped the nucleus the way Yukawa's messenger must. The physicists who went looking did not have accelerators powerful enough to make such particles on demand. They had to look where nature was already making them, in the steady, invisible rain of particles that falls on the Earth from space every second of every day. That rain is where the story goes next, up to mountaintops and into the high, cold air. Every second, day and night, a fine rain falls on the Earth from above. You cannot feel it or see it. but it passes through your body, through the roof, through the ground beneath you, constantly. It is a rain of particles, born when fragments of matter from distant space, some flung out by exploding stars, come streaming into the top of the atmosphere at tremendous speed and smash into the air. Physicists call the incoming fragments cosmic rays, and the collisions high overhead shower down a spray of new particles, some of which reach the ground. In the 1930s, before machines could make exotic particles, this rain was the only place to find them, so physicists climbed. They carried their instruments up mountains, where the air was thinner and the rain less filtered, closer to where the collisions happened. The instrument of the day was the cloud chamber, a sealed box of moist air arranged so that a passing charged particle would leave a thin trail of droplets behind it, like the white line a high airplane draws across the sky. By placing a magnet around the chamber, physicists could bend those trails. A particle's path curved in the magnetic field, and the amount and direction of the curve revealed its charge and, with care, its weight. Lighter particles curved tightly. Heavier ones swept through in a lazier arc. In 1936 and 37, two physicists in the United States, Carl Anderson and Seth Neddermeyer, were studying these cosmic ray trails at altitude. Anderson already had a great discovery behind him. A few years earlier, he had found the anti-electron, the first piece of antimatter ever seen, in just this kind of chamber. Now, sorting through the curved tracks, he and Neddermeyer kept finding a particle that did not fit the two kinds they knew. It was not a light, sharply curving electron. It was not a heavy proton. It bent in the field as though it weighed something in between, in the middle range, a couple 100 times the electron's weight. A middleweight particle, the very thing Yukawa had predicted 2 years before, of roughly the very weight he had named. To the physicists who knew of Yukawa's idea, the conclusion seemed almost to leap off the photographs. Here, raining down from the sky, was the messenger of the strong force. The prediction and the discovery matched in the one number that could be measured, the weight, and that match was thrilling. For a decade, much of the physics world believed the carrier of the nuclear force had been found in the cosmic rain. The new particle was given a name. After some wandering, it came to be called the mu meson, and later simply the muon. It seemed to be Yukawa's particle wearing a slightly different name, the heavy messenger come down from the sky to confirm a beautiful idea. Yukawa's reputation rose on the strength of it. The reach of the force had predicted a weight. The weight had been found, and the circle looked closed. But a weight is only one fact about a particle, and a particle is more than its weight. Yukawa's messenger was not defined by its mass alone. It had a job to do. It was supposed to be the carrier of the strong force, which meant that above all else it had to feel that force fiercely. It had to be drawn to nuclei, to be gripped by them, to dive into protons and neutrons and bind them. The muon had the right weight. Whether it had the right behaviour, whether it actually gripped the nucleus the way Yukawa's messenger must, was a separate question, and for years no one pressed it hard enough to notice the answer was wrong. When physicists finally did press it, near the end of the Second World War, the answer broke the beautiful picture wide open. The middleweight particle from the sky, it turned out, barely noticed the nucleus at all. The test that broke the picture was, on its face, simple. If the muon was the carrier of the strong force, then it must feel that force strongly. So take a muon, bring it to rest inside ordinary matter, right among the nuclei, and watch what happens. A particle that carries the strong force, pulled in close to a nucleus, should be seized by it almost instantly, swallowed up before it has any chance to do anything else. That capture should be lightning fast, faster than almost any other process the particle could undergo. There was a complication. A muon carrying negative charge would be drawn toward the positive nucleus by ordinary electricity too, quite apart from the strong force, and could be captured that way. So the cleanest test used the difference between negative and positive muons. A negative muon, attracted to the nucleus, could in principle be caught by either force. A positive muon, pushed away from the positive nucleus by electricity, would be held off, kept at a distance, and could only reach the nucleus if the strong force reached out and dragged it in. If the muon felt the strong force, even the positive ones should eventually be pulled into nuclei. If it did not, the positive ones would simply sit, ignored, and decay on their own slow schedule. In Rome, during and just after the war, 3 physicists set out to do this experiment under terrible conditions. Their names were Marcello Conversi, Ettore Pancini, and Oreste Piccioni. The war was all around them. Pancini was active in the Italian resistance and was pulled away from the work for a time. They moved their equipment to escape the bombing, once to the relative safety of a basement near the Vatican. With improvised apparatus and great patience, they sorted muons by their charge and watched what the nuclei did with them. The result, published in 1946, was quietly devastating. The positive muons behaved as expected, decaying on their own. But the negative muons, the ones drawn right up against the nucleus, did not get swallowed the way a strong force particle should. In light elements, they too simply decayed, sitting beside the nucleus for an enormously long time, on the scale of these things, without being captured by the strong force at all. The muon, brought to the very doorstep of the nucleus, did not feel the grip. It lingered, untouched, where Yukawa's messenger should have been seized in an instant. The mismatch was not small. The muon ignored the strong force by a factor so large that there was no explaining it away as a slow version of the right behaviour. A later calculation by the physicists Enrico Fermi, Edward Teller, and Victor Weisskopf drove the point home, showing the muon's reluctance to be captured was off from Yukawa's prediction by something like 1 trillion times. This was not the carrier of the strong force. This was a particle that happened to have nearly the right weight and almost nothing else in common with what Yukawa needed. It had the body of the messenger and none of its purpose. So physics was left with deep confusion. Yukawa's logic still looked sound. The strong force really did seem to need a heavy messenger of about that weight. And the cosmic rain really did contain a particle of about that weight. But that particle was the wrong one. It would not do the job. Either Yukawa was wrong, or there was a second middleweight particle out there, the real messenger, hiding behind the imposter that had been mistaken for it. The answer turned out to be the second, and a few physicists had already begun to suspect it. The way out was to stop assuming there was only one particle in that middle range. Perhaps there were 2, born one from the other, so alike in weight that the cloud chambers had blurred them into a single thing. Pulling those 2 apart in idea and then in fact is what finally set the story straight. The way out of the confusion was an idea before it was a discovery, and it came from more than one direction at once. If the particle found in the cosmic rain had the right weight, but the wrong behaviour, perhaps it was not Yukawa's messenger at all, but the offspring of Yukawa's messenger. Perhaps there were 2 middleweight particles, not one. The first, the true carrier of the strong force, would be made high in the atmosphere and would feel the nucleus fiercely. But feeling the nucleus fiercely also meant it would be short-lived, quick to interact and quick to fall apart, decaying almost as soon as it was born. When it decayed, it could give birth to the second particle, lighter, longer-lived, and indifferent to the strong force, and it was this second particle, the daughter, that survived the long fall through the atmosphere to reach the cloud chambers below. This was the 2 meson idea, one heavy parent that carried the force and died young, high up, one lighter daughter that carried nothing and lived long enough to be caught, the cosmic ray particle that Anderson and Neddermeyer found, and that Conversi, Pancini and Piccioni showed to ignore the nucleus, was the daughter. Yukawa's real messenger, the parent, had been decaying away in the upper air all along, never reaching the instruments, hidden behind the child it left behind. Several physicists arrived at versions of this resolution. In Japan, working in near isolation during the war, Shoichi Sakata and others had proposed that the carrier and the particle seen at ground level were different things. In the West, the physicist Robert Marshak laid out the 2 meson idea clearly in 1947, reasoning that the particle reaching the ground could not be the one Yukawa needed. and that a heavier parent must exist above it. The logic was the same from both sides. Save Yukawa's idea by splitting the single confusing particle into two, a strongly interacting parent and a weakly interacting child. It was an elegant escape, but elegance is not evidence. An idea that two particles existed, where the experiments had seen only one, needed to be proven by actually catching both, by separating them in the data and showing the parent turning into the child with your own eyes. The cloud chambers had not managed it. Their trails were too coarse, the two particles too close in weight, the moment of decay too fleeting and too high up to catch. To see one meson become another, physicists needed a finer eye, a recording medium that could freeze the act of decay in fine detail and hold it still for study. That finer eye already existed, in an old and humble technology that was about to be perfected. It was photographic emulsion, the same light-sensitive coating used in ordinary film but made thick and specially prepared. When a charged particle passed through such an emulsion, it disturbed the grains along its path, and when the film was developed, those grains turned dark, leaving a permanent track, a line of black specks recording exactly where the particle had gone. Unlike a cloud chamber, which had to be triggered at the right instant, an emulsion plate sat exposed for weeks, patiently catching everything that passed through and held the result forever. A particle coming to rest and decaying into another would leave an unmistakable signature in such an emulsion. One track would end, and from its very end point a second track would begin, fainter or heavier as the new particle's weight dictated, kinked away at an angle. A parent becoming a child, frozen in the film as two lines meeting at a point. If the two meson idea was right, that double track was waiting to be found in emulsions exposed high enough where the parent particles had not yet all decayed away. So the search moved again to the mountains, with plates instead of chambers, carried high to thin air and left to drink in the cosmic rain. In 1947, in emulsions exposed on a peak in the Pyrenees and in the Andes, the double track appeared, and Yukawa's true messenger finally stepped out of hiding. The breakthrough came from a laboratory in Bristol, England, led by a physicist named Cecil Powell. Powell had spent years patiently refining the photographic emulsion method, turning a crude technique into a precise tool. Working with him were Giuseppe Occhialini, an Italian physicist of restless energy who had fled fascism and helped drive the work forward, and Cesar Lattes, a young Brazilian physicist whose role in what followed was central. Their plan was direct. Make the emulsions as sensitive as possible, carry them as high as possible, and read the tracks with painstaking care under the microscope. Height mattered because of the two meson idea. The true messenger, the parent particle, decayed quickly, so it had to be caught high up before it vanished. Lattes arranged for plates to be exposed at a mountain observatory in the Pyrenees, and then, reaching for greater altitude at a station high in the Andes of Bolivia, more than 15,000 feet above the sea. The thin air there let far more of the parent particle survive to reach the film. The exposed plates were carried back to Bristol, developed, and handed to a team of microscope readers who scanned them inch by inch, tracing every track by eye. What they found in 1947 was exactly the double track the idea had predicted. A particle would come to rest in the emulsion, its track thickening and stopping, and from that stopping point, a second track set off at an angle, the mark of a new, lighter particle born from the first. One meson had decayed into another, frozen in the film as two lines meeting at a kink. The parent they named the P meson, soon shortened to Pion. The lighter daughter was the particle already known from the cosmic rain, the mu meson, the muon. The Pion decayed into the muon, parent and child caught together at last. The Pion was Yukawa's particle. It had the right weight, a little heavier than the muon in the middle range Yukawa had named. More importantly, it had the right behavior. Further study showed the Pion was born in the violent nuclear collisions of cosmic rays and felt the strong force fiercely, exactly as the carrier of that force must, It interacted with nuclei eagerly, where the muon had ignored them. The body and the purpose finally lived in the same particle. 12 years after Yukawa put it on paper, his messenger had been seen. The discovery settled the long confusion in a single stroke. The middleweight particle of the cosmic rain had been two particles all along, just as the two-meson idea proposed. The strongly interacting parent, the Pion, was Yukawa's messenger, made high in the air and quick to decay. The weakly interacting daughter, the muon, was something else entirely, a particle with no role in holding the nucleus together, which had been mistaken for the messenger only because it shared nearly the same weight and reached the ground while its parent did not. The recognition came quickly. Yukawa received the Nobel Prize in 1949, the first Japanese person to be so honoured for predicting the meson more than a decade before it was confirmed. Cecil Powell received the prize in 1950 for developing the emulsion method and discovering the Pion with it. The young idea from a man working alone in Japan, dismissed or ignored for years, had been vindicated by tracks of dark grains in film exposed on a mountaintop, and the muon, the wrong visitor, did not go away. It remained a genuine puzzle in its own right, a particle that seemed to be a heavier copy of the electron, with no obvious reason to exist. Years later, one physicist would famously wonder aloud who had ordered it. But that is a different thread. The thread we're following had found its particle, and now the work could begin of understanding what this small, fleeting thing actually was. Once physicists could make and study pions in earnest, especially after new accelerators began producing them in great numbers, the pion turned out not to be a single particle, but a small family of three closely related ones. They differ in their electric charge. There is a positively charged pion, a negatively charged pion, and a neutral pion carrying no charge at all. The three are so alike in other ways that physicists treat them as three faces of one thing, but their differences matter, and the neutral one in particular behaves in a way worth dwelling on. The charged pions, positive and negative, are near mirror images of each other. They have the same weight, the same lifetime, and opposite charge, the way an electron and its antimatter twin mirror each other. Each is the antiparticle of the other. The positive pion and the negative pion are a particle and its anti-twin. They weigh a little more than 270 times the electron, putting them squarely in the middle range Yukawa had foreseen, and they are not stable. A charged pion left alone survives for only a tiny fraction of a second before it decays, transforming mostly into a muon and a near-weightless partner particle. That decay, pion into muon, was exactly the double track seen in the Bristol emulsions. The neutral pion is the odd member of the family. It is slightly lighter than its charged siblings, and it lives a far shorter life, vanishing almost the instant it forms, and it does not decay into a muon. Instead, the neutral pion disappears in a flash of pure light. It turns into two photons, two packets of high-energy light flying apart in opposite directions. A small piece of matter, born in a nuclear collision, simply converts its entire substance into light and is gone. The neutral pion is, in a real sense, a particle that ends its brief life as a burst of radiance. This flash into light is not a quirk to pass over. It is a window into what the pion is made of, though that understanding would come later. For now, hold the image. The charged pions decay into other particles of matter. The neutral pion decays into light itself, two photons born from the death of one particle, in a time so short it is hard to find words small enough for it. If a charged pion's life is a flicker, the neutral pion's life is a flicker of that flicker. The three pions together form what physicists came to call a triplet, three particles so similar that nature seems to regard them as one underlying thing wearing three different charges. This near sameness was itself a clue, hinting that charge was almost an afterthought to the pion, a label that could be swapped without changing the particle's deeper nature. That hint would grow into one of the organizing ideas of nuclear physics, the notion that the proton and neutron too are nearly the same thing wearing different charges, and that the pions are the particles that turn one into the other, You can already see the shape of how the pions do their job. With 3 charges available, a pion can carry charge from one particle to another as it passes between them. A positive pion thrown from a proton can land on a neutron and change what it is. The family of 3 is exactly what you need to let protons and neutrons trade identities while they trade the force, and that trading turns out to be central to how the strong force binds the nucleus. So the messenger Yukawa imagined arrived not as one particle but as a matched set of 3 2-charged mirror twins and one neutral sibling that dies in a flash of light. With the family known, the next task was to pin down the pion's basic traits cleanly, to say plainly what kind of thing it is before following it back into the nucleus to watch it work. It helps now to gather the pion's basic traits in one place and state plainly what kind of thing it is, the way you would describe an animal by its size, its habits, and its lifespan. The pion is small, simple, and fleeting, and each of those qualities shapes the role it plays. Start with weight, the trait that began the whole story. The pion is the lightest of the mesons, the lightest member of its whole class of particles. A charged pion weighs about 273 times what an electron weighs, and the neutral one a little less. Set against a proton, though, the pion is light, only about 1/7 of the proton's weight, so it sits in the middle, heavier than the electron by a lot, lighter than the proton by a fair amount, just where Yukawa placed his messenger. Being the lightest meson matters, because the lightest messenger reaches the farthest, and so the pion is the part of the strong force that reaches out the longest distance between nucleons. Next, its spin. Every particle carries a kind of built-in rotation that physicists call spin, a fixed amount that never changes for a given type of particle. The pion's spin is 0. It is one of the simplest possible cases, a particle with no built-in rotation at all, no internal sense of direction from spinning. This makes the pion what is called a scalar particle, the plainest kind, and it simplifies how the pion behaves when it passes between nucleons. A spin-0 messenger is in some ways the most basic force carrier imaginable. Then its lifetime, which is short past easy imagining. A charged pion lives for about 26 billionths of a second before it decays. That sounds like nothing, and it is, by the clock of a human life. But to a pion, it is a long and full life, long enough to fly some distance, long enough to do its work passing between nucleons many times over. The neutral pion lives far shorter still, only a few billionths of the time its charged siblings last, before it flashes into 2 photons. Both are fleeting, but the neutral pion is fleeting on a scale that dwarfs even its charged siblings' brief span. From these traits comes the pion's whole manner of being. It is born in violent collisions, where enough energy is gathered in one place to call its mass into existence out of that energy. It lives its tiny life, perhaps passing between a proton and a neutron, perhaps flying free for a moment. Then it decays, the charged ones into muons and the neutral ones into light, returning its borrowed substance to the world. It is not a permanent brick of matter like the proton, which can sit unchanged for longer than the age of the universe. It is a transient, a particle that flashes into being, does its work, and is gone. That transience is the key to its role as a messenger. Recall the borrowing rule, the loan of energy that must be repaid fast. Inside the nucleus, a pion is most often a virtual particle, borrowed from nothing for the briefest instant as it crosses between 2 nucleons, never truly free, paid back before it can be seen. The real pions made in collisions, the ones that live their 26 billionths of a second and leave tracks in emulsion, are the same particle caught in the open, given enough energy to exist on its own for a while, rather than only as a fleeting loan. Studying those free pions taught physicists the traits of the hidden, borrowed ones that do the binding. So that is the pion. Lightest of the mesons, 1/7 the weight of a proton. Spinless, the simplest kind of force carrier. Fleeting, born in violence and gone in a flash, whether into a muon or into light. With these plain facts in hand, we can finally do what Yukawa set out to do in the first place. We can take a single pion and watch it pass between a proton and a neutron and see the strong force at work in its simplest form. To watch the pion do its job, go to the simplest place it works, the smallest nucleus that holds more than one piece. Hydrogen's ordinary nucleus is a single proton, alone, with nothing to bind. But there is a heavier form of hydrogen, called deuterium, whose nucleus holds two particles, one proton and one neutron, bound together. This two-piece nucleus is named the deuteron, and it is the cleanest laboratory in nature for seeing the strong force act between just two nucleons, with no crowd to complicate the picture. The deuteron is barely bound. It is held together, but only just by the gentlest grip the strong force ever manages between two nucleons. Pull on a deuteron with a modest amount of energy, and it comes apart into its proton and neutron. This fragility is itself revealing. The strong force, so overwhelmingly fierce up close, produces in the deuteron only a faint binding, because the proton and neutron sit a little apart, near the outer edge of the force's short reach, where it has weakened. The deuteron lives at the gentle rim of the strong force, not in its fierce heart. In Yukawa's picture, what holds the deuteron together is the constant trade of pions between the proton and the neutron. The proton emits a pion. The neutron absorbs it. A moment later, the neutron emits one and the proton absorbs it. Back and forth the pions fly, borrowed and repaid, and this endless exchange is the force. Each pion is a virtual particle, never seen, living only the borrowed instant it takes to cross the tiny gap between the two nucleons. The proton and neutron are bound because they are forever passing this messenger between them, a game of catch so fast and so small that from outside it looks simply like attraction. There is a way to picture two things held by something passed between them. Imagine two people standing on slippery ice, tossing a heavy ball back and forth. Throwing and catching the ball, you might expect, would push them apart, and for some kinds of exchange it does. But the strong force exchange works the other way, drawing them together as if each throw and catch tug the two a little closer rather than shoving them away. The comparison is rough, and it breaks down quickly, because a virtual pion is nothing like a ball you can see, and the binding it makes is attractive in a way the simple picture cannot quite explain. Still, it carries the core idea, a force made not by reaching across a gap but by something physically passing through it. Where the ball picture fails is exactly where the real physics gets interesting. A thrown ball is a real object moving from one hand to the other. A virtual pion is alone, called into being from nothing and erased before it can be caught, existing only because the borrowing rule allows it for an instant. You can never intercept it. If you tried to catch a pion mid-exchange, you would have to supply the energy to make it real, and then it would no longer be the hidden messenger but a free particle flying off on its own. The force lives precisely in what cannot be seen, in the borrowed and repaid, and that is why it took a Yukawa to imagine it rather than an eye to see it. The deuteron, then, is the strong force at its simplest and most honest. One proton, one neutron, bound by the exchange of pions across the small gap between them, held loosely at the rim of the force's reach. Everything larger, every heavier nucleus, is in some sense built from many such pairings layered together, each nucleon trading pions with its near neighbours. Understand the deuteron and you hold the seed of all nuclear binding. But the pion does more than pass quietly between a proton and a neutron. When a charged pion makes the trip, something stranger happens. The proton and the neutron trade more than the force. They trade their very identities, and that trading opens the next idea. Look again at a charged pion crossing between a proton and a neutron, and follow the charge. A proton carries positive charge. A neutron carries none. Suppose the proton emits a positive pion, handing off its positive charge to the messenger. Having given away its positive charge, the proton is no longer a proton. It has become a neutron. The positive pion flies across and is absorbed by the neutron on the other side. Having taken on that positive charge, the neutron is no longer a neutron, it has become a proton. In a single exchange, the two particles have swapped identities. The proton became a neutron, and the neutron became a proton, and a pion carried the change across the gap. This is a remarkable thing to sit with. The proton and the neutron are not fixed, separate kinds of matter, sealed off from each other. Inside the nucleus, they are constantly turning into one another, trading places as charged pions pass between them. What looks from outside like a stable nucleus of fixed protons and neutrons is, up close, a shimmering exchange in which the particles are forever swapping which is which. The identities blur. A given particle is a proton this instant and a neutron the next, depending on the pion just thrown or caught. This blurring led physicists to a powerful idea, one that had been planted even before the pion was found. As early as 1932, soon after the neutron's discovery, Werner Heisenberg suggested that the proton and the neutron might be regarded as two states of a single underlying particle. They weigh almost exactly the same, the neutron only a touch heavier. Apart from charge, they behave almost identically under the strong force. So perhaps, Heisenberg proposed, the strong force does not really distinguish them at all. Perhaps proton and neutron are like a single coin showing heads or tails, one particle, the nucleon, wearing one of two faces. To capture this, physicists borrowed the mathematics of spin and applied it to identity itself, giving the idea the name isospin. The word is a kind of pun. It is not real spin, not actual rotation, but the bookkeeping works the same way. Just as an electron spin can point up or down, a nucleon's isospin can point one way to make it a proton, the other way to make it a neutron. Flipping the isospin turns one into the other, and a charged pion is exactly the thing that does the flipping. The pions themselves carry isospin too, the three of them forming a natural set, positive, neutral and negative, just right for nudging nucleons from one identity to the other. Isospin was more than a tidy relabeling. It was a near symmetry of nature, a sign that the strong force is almost blind to the difference between a proton and a neutron. If you could switch every proton in a nucleus to a neutron and every neutron to a proton, the strong force would behave almost exactly as before. The symmetry is not perfect, because the proton and neutron differ slightly in weight and in charge, but it is close enough to be one of the most useful guides physicists had. It let them predict how pions and nucleons would interact by treating proton, neutron, and the three pions as members of orderly families related by isospin. The deeper meaning of isospin would not become clear until physicists looked inside the proton and neutron and found what makes them nearly identical, a story still several chapters away. For now, the lesson is that the pion does not merely bind the nucleus. It animates it, turning protons into neutrons and back in a ceaseless exchange, revealing that the two are nearly the same thing seen from two sides. The nucleus is not a still pile of fixed pieces, it is a living trade, and when physicists began firing pions directly at nucleons to study this trade head-on, they found something new hiding in the collisions, a fleeting heavier state that appeared whenever a pion and a nucleon met with just the right energy. That state would crack the door open to a whole hidden world. By the early 1950s, physicists no longer had to wait for pions to fall from the sky. New machines called accelerators could produce them in controlled beams, streams of pions that could be aimed at a target and studied. One of the great early experiments of this kind was carried out by Enrico Fermi and his colleagues at the University of Chicago, using a beam of pions fired at hydrogen, which is to say at protons. The question was simple. When a pion strikes a proton, what happens, and how does it depend on the energy of the collision? Fermi measured how often the pion scattered off the protons as he tuned the energy of the beam up and down. If pions and protons simply bounced off one another like hard little balls, the scattering would change smoothly and gently with energy, with nothing special happening at any particular point. That is not what Fermi found. As he raised the energy, the scattering grew stronger, then surged to a sharp peak at one particular energy, then fell away again. At that special energy, pions and protons interacted far more eagerly than at any energy nearby. Something about that exact energy was special. A sharp peak like this, where particles interact far more strongly at one precise energy, is the fingerprint of what physicists call a resonance. It means that at that energy, the pion and the proton are not merely glancing off each other. For a fleeting instant they join, combining into a single new particle, a heavier and very short-lived thing that exists for the briefest moment before breaking apart again into a pion and a nucleon. The peak marks the energy needed to call that heavier particle into being. The new particle that emerged from Fermi's peak came to be called the delta. The delta is a heavier sibling of the proton and neutron, built from the same kind of stuff but carrying more energy and a different internal arrangement. It weighs about a third more than a proton, and it lives an almost unimaginably short life, forming and decaying so fast that it can never travel any real distance. It is less a lasting particle than a momentary state, a brief resonance of pion and nucleon. Yet it was unmistakably real, announced by that clean, strong peak in Fermi's data, and it carried a heavy hint inside it. The hint was this: if the proton and neutron can have a heavier sibling like the delta, then they are not the simplest, most basic objects in nature. A truly fundamental particle, with no parts inside, does not have heavier versions of itself. There is nothing inside it to rearrange into a higher energy form. The delta looked exactly like a proton, with its inside stirred into a more energetic pattern, the way a struck bell rings at a higher tone. And if the proton could be stirred into a delta, then the proton must have insides to stir. It must be built from smaller parts. The same lesson came from the pion side. The pion too turned out to have heavier siblings, other mesons that appeared as resonances at higher energies, heavier patterns of whatever the pion was made from. Neither the pion nor the nucleon was looking like a simple, partless point. Both were behaving like composite things, objects with internal structure that could be excited into heavier forms, the way an atom can be excited into higher energy states by stirring its electrons. Fermi's peak, then, was more than a measurement of pion scattering. It was an early sign that the whole growing collection of particles, the nucleons and the pions, and now the delta, shared some hidden inner construction. The strong force was not a relationship between simple, fundamental bricks. It was something happening among objects that themselves had parts. But before anyone could find those parts, the situation got much worse, because the accelerators kept running, and they kept finding new particles, dozens of them, until the orderly picture collapsed into a bewildering crowd. Through the 1950s and into the 60s, the accelerators grew more powerful, and the number of known particles exploded. It had begun so neatly. The proton, the neutron, the electron, the photon, and Yukawa's pion, a short, manageable list. Then the delta arrived from Fermi's peak, then more resonances, more short-lived heavy siblings of the nucleon, then strange new particles that appeared in cosmic rays and accelerators and decayed in unexpectedly slow ways, earning the very name strange. Particle after particle, until the count climbed past 100, then kept climbing. It became a flood. Physicists found themselves drowning in particles, each with its own weight, charge, spin, and lifetime, and no clear reason for any of them to exist. There were so many that one senior physicist, Wolfgang Pauli, grumbled that physics was coming to resemble botany, the mere cataloguing of specimens rather than a science that explained. Enrico Fermi reportedly told a young researcher that if he had known there would be so many particles, he would have become a botanist instead of a physicist. The particles were given Greek letters and names until the alphabet strained under them. The proud simplicity of the early picture was gone, and the pion, once the exotic newcomer, now looked almost humble in the crowd. It was no longer a strange prediction vindicated on a mountaintop. It was the lightest member of a vast and growing family of mesons, just one entry in a swelling catalogue. The same was true of the proton and neutron. now seen as the lightest members of an even larger family that included the delta and many heavier cousins. Everywhere physicists looked, the particles came not as lonely individuals but in groups, in families, with patterns of weight and charge that hinted at some order beneath. That hint of order was the way out of the flood, though it took years to read. The particles were too many to be fundamental. Nature does not build the world from hundreds of equally basic bricks. That is not how the deepest layers had ever worked before. The sheer number was itself the clue. When the chemical elements had once seemed a bewildering list, the periodic table had revealed an order beneath them, and that order had pointed to a smaller set of parts, the protons and electrons, from which all the elements were built. The flood of particles cried out for the same kind of resolution. There had to be a smaller set of truly basic pieces, and the 100 particles had to be different combinations of them. Physicists began to look for the pattern in earnest, sorting the particles into families by their properties, and searching for the simple scheme that would explain why those families had the shapes they did. The work was like arranging the flood of specimens until the underlying logic showed through, the way scattered facts about the elements had once arranged themselves into rows and columns. The mesons, the Pion among them, fell into neat geometric patterns when plotted by their properties. So did the nucleons and their heavier kin. The patterns were too clean to be accidents. They pointed unmistakably to a hidden inner structure shared by all of them. The Pion was about to be revealed as something it had never been suspected to be. Yukawa's messenger, the carrier of the nuclear force, the particle that bound the deuteron and turned protons into neutrons, was not a basic piece of nature at all. Like the proton, like the neutron, like the whole flood of new particles, it was built from something smaller, something that had never been seen alone and never would be. The order beneath the flood was about to name those smaller things, and in doing so it would turn the entire story of the nucleus inside out. The Pion, and everything around it, was about to be rebuilt from parts no one had yet held. The order beneath the flood was found, on paper, in 1964, by two physicists working independently. One was Murray Gell-Mann at the California Institute of Technology, a man of dazzling range and sharp tongue who had already done much to sort the particles into families. The other was George Zweig, a young physicist then at the European Laboratory in Geneva, who arrived at nearly the same idea on his own. Each proposed that the 100-odd particles were not fundamental at all, but were built from a small number of deeper pieces. Gell-Mann gave those pieces a strange, playful name taken from a line in a novel. He called them quarks. The scheme was beautifully simple in outline. There were at first 3 kinds of quark, and from them the whole flood could be built. The proton and neutron were each made of 3 quarks bound together. The mesons, including the Pion, were made differently, from just 2 pieces, a quark and an antiquark, a quark paired with its own antimatter twin. Every particle in the bewildering catalogue was some combination of these few quarks, the way every word on a page is a combination of a few letters. The patterns physicists had seen, the neat geometric families, were simply the different ways the quarks could be arranged. For the Pion, this meant a new and humbler identity. Yukawa's messenger, the carrier of the nuclear force, was a quark bound to an antiquark, the simplest possible meson. The positive Pion was one kind of quark joined to a particular antiquark. The negative Pion was the mirror of that pairing. The neutral Pion was a blend of quark-antiquark pairs. The Pion's smallness in the family, its position as the lightest meson, now had a reason. It was among the lightest things you could build from a quark and an antiquark. This also explained at last why the proton could be stirred into a delta. A proton is 3 quarks in their calmest arrangement. Strike it hard enough and the quarks shift into a more energetic pattern, and that excited arrangement is the delta. The bell had insides to ring after all, and the insides were quarks. The same logic explained the heavier mesons as excited arrangements of a quark and an antiquark. The whole flood drained into a few quarks combined in different ways and stirred to different energies. There was one deeply strange feature, and physicists struggled with it for years. No one could knock a quark loose. However hard the accelerator struck a proton, no single quark ever came flying out to be caught and weighed on its own. The quarks seemed permanently locked inside the particles they composed, never to be seen in isolation. This was so unlike anything before it that many physicists at first doubted quarks were real things at all, rather than a convenient bookkeeping trick. Gell-Mann himself was for a time cautious about whether quarks existed as actual objects or only as a useful pattern. The doubt did not last. Through the late 1960s, experiments at a long accelerator in California fired electrons deep into protons and watched how they bounced. The electrons sometimes ricocheted sharply, as though they had struck small hard lumps inside the proton rather than passing through a soft uniform blob. The proton had internal grains, hard scattering centers, just as quarks predicted. The pieces could not be pried out, but they could be felt inside, the way you might sense pebbles inside a sealed bag by the way it deforms under your fingers. So the Pion, and everything else, was built from quarks that could never be set free. This raised a sharp new question, sharper than before. If quarks are locked inside particles by some force, what is that force, and why does it never let go? Yukawa's Pion exchange had explained how nucleons bind to one another, but the quarks inside each nucleon were held by something else, something deeper and stranger, a force unlike any seen before. That deeper force is where we turn next. The force that binds quarks inside a proton is the true strong force, and it is stranger than anything Yukawa imagined. To describe it, physicists had to invent a new kind of charge, unlike electric charge, and they gave it a whimsical name. They called it color. It has nothing to do with the colors your eyes see. The name is a label, chosen because the rules of how the charges combine resemble the way colors of light blend to white. Each quark carries one of 3 color charges, and the rule of nature is that quarks must always combine so their colors cancel to neutral, the way 3 colored lights can blend to colorless white. This is why a proton holds exactly 3 quarks, one of each color, balancing to neutral. And it is why a meson like the Pion holds a quark and an antiquark, a color and its matching anticolor, again cancelling to neutral. The rule that everything in nature must be color-neutral shapes which combinations of quarks can exist. The flood of particles was, in the end, a catalogue of all the color-neutral arrangements you can build. The force between color charges is carried by a messenger, just as the electric force is carried by the photon. The messengers of the color force are called gluons, because they glue the quarks together. But here the new force does something the electric force never does. The photon that carries electricity has no electric charge of its own. Light is electrically neutral. The gluons that carry the color force do carry color charge themselves. The messengers are charged, and that single difference changes everything. Because gluons carry color, they pull on one another, not only on the quarks. The force does not simply spread out from a quark and thin away. It gathers itself into tight tubes of force running between the quarks, ropes of pure interaction that do not weaken with distance the way electricity does. Pull 2 quarks apart, and the rope between them does not fade. It stays taut, and the energy stored in it grows the farther you pull, like stretching a band that never slackens. This is why no quark ever comes loose. To separate 2 quarks fully would take infinite energy, and long before you reached it, the energy poured into the rope would conjure new quarks out of nothing, fresh particles that cap the broken ends. You can never hold a lone quark, only ever new particles born from the attempt. This complete theory of quarks, color and gluons is called quantum chromodynamics, from the Greek word for color. It is the real theory of the strong force, the deepest layer, replacing the rough picture of nucleons trading pions with a truer picture of quarks trading gluons. The fierce force that holds the nucleus together, the thing Yukawa first glimpsed, is at bottom this: quarks bound by gluons into protons and neutrons, by a force that grows stronger, not weaker, as you try to pull it apart. There is a second oddity, the mirror of the first. While the force grows strong at long range, locking quarks in, it grows weak at very short range. Quarks squeezed close together inside a proton feel the colour force only faintly and move almost freely in the tight space. This strange freedom up close, called asymptotic freedom, was worked out in 1973 and earned its discoverers the highest recognition. The colour force is gentle when quarks are near and ferocious when they part, the exact opposite of every force in ordinary life. So beneath Yukawa's Pion lies a deeper world, quarks chained by colour through gluons that bind themselves. The question now becomes urgent. If this is the real strong force, the one acting between quarks, then what is Yukawa's force, the pull between whole nucleons? It must be something that leaks out of this deeper force, a remnant of it, and a remnant is exactly what it turned out to be. If the true strong force acts between quarks, binding them into protons and neutrons, then the force that holds those protons and neutrons together in a nucleus must be something else, something secondary. A proton is colour neutral. Its three colours cancel to nothing. From outside, it shows no colour charge at all. So why should one colour-neutral proton feel any colour force from another colour-neutral neutron sitting beside it? By the strict rule, neutral things should not pull on each other through the colour force at all, and yet they do, faintly. The answer is that the proton, while neutral overall, is not empty inside. Its quarks and gluons are in constant motion, and the colour force does not cancel perfectly at every point within it. Just outside the proton's edge, a small amount of colour force leaks out, a faint residue of the powerful force raging within. When another nucleon comes very close, it feels this leakage. The pull between nucleons is the spillover of the colour force, the small part that does not quite cancel, reaching just past the surface of each neutral particle. This is what Yukawa's Pion exchange really is. When physicists watch a pion pass between a proton and a neutron, they are watching the leakage in action, the residual colour force made visible as the exchange of a quark-antiquark pair. The pion, being itself a quark and an antiquark, is exactly the kind of object that can carry colour force across the small gap between two nucleons, while staying colour neutral on the trip. Yukawa's picture was not wrong. It was a true description of the residue, written before anyone knew there was a deeper force for it to be a residue of. There is a familiar parallel that makes this leftover force easier to hold. Think of ordinary atoms, each electrically neutral, with its negative electrons exactly balancing its positive nucleus. From a distance, an atom shows no electric charge, and two neutral atoms should ignore each other. Yet they do not quite. Up close, the charges inside each atom shift and slosh, and for an instant one side of an atom is slightly more negative, the other slightly more positive. This fleeting imbalance tugs on a neighbouring atom, and a faint attraction arises between them, even though both are neutral overall. That weak attraction between neutral atoms is what lets gases cool into liquids, what makes water bead and cling. The nuclear force is the same kind of thing, one layer down. Just as a faint electric residue draws neutral atoms together, a faint colour residue draws neutral nucleons together. The cling between water molecules and the grip that holds the nucleus are cousins, both leftover forces, both the small, uncancelled remainder of a deeper attraction between the charged pieces inside. The nucleus is bound by the crumbs of the colour force, the part that escapes the otherwise perfect cancellation within each nucleon. This recasts the entire story of the nucleus. The strong force that holds the centre of the atom together, the force that overpowers electricity and keeps matter from flying apart, is not a fundamental force in its own right. It is a shadow of the real strong force, the colour force between quarks. It is fierce only because the force it descends from is so much fiercer still that even its leftover crumbs outmuscle electricity. The grip on your stone is a residue of a deeper grip you can never see directly. And this leftover nature explains the strange manners from the beginning, the short reach, and the saturation, more deeply than Yukawa could. the force is short-ranged because a residue, a near cancellation, dies off quickly with distance. It saturates because, like the cling between molecules, each nucleon binds only to those it touches. The odd manners were the signature of a leftover force all along. But the deeper force holds one more surprise, hidden in the very weight of the proton, and it is the strangest of all. Here is a fact about the proton that seems impossible when you first meet it. A proton is made of 3 quarks. You would expect, then, that the weight of the proton is just the weight of its 3 quarks added together, the way the weight of a bag of marbles is the weight of the marbles inside. It is not. If you add up the weights of the 3 quarks inside a proton, they account for only a tiny sliver of the proton's total mass, around 1 part in 100. Nearly all the weight of the proton, 99 parts in 100, comes from somewhere else. Where does it come from? It comes from energy. The quarks inside a proton are not sitting still. They move at nearly the speed of light, racing within their tiny prison, and the gluons binding them carry enormous energy in those taut ropes of colour force. By the deep link between energy and mass, that energy has weight. Energy and mass are 2 names for the same thing, joined by the most famous equation in physics, which says that energy locked inside a thing shows up as part of its mass. The roiling energy of the quark's motion and the gluon's binding is the overwhelming bulk of the proton's mass. Sit with what this means. You, your body, the stone, the earth, the stars, are made mostly of protons and neutrons, and the mass of those protons and neutrons, the heaviness of nearly everything you have ever lifted, is almost entirely energy, not the weight of any solid pieces inside. The quarks, the actual bits of matter, contribute almost nothing to the total. When you feel the weight of the stone in your hand, you are feeling, almost entirely, the bottled energy of colour force, the motion and binding of quarks, given heaviness by the equivalence of energy and mass. This overturns the oldest intuition about weight. We imagine that a heavy thing is heavy because it is made of heavy stuff, that mass is a measure of how much solid substance is packed inside. At the deepest level, that is false. Mass is mostly motion and binding. The proton weighs what it does not because its quarks are heavy, but because the energy of the strong force inside it is so vast, and that energy weighs. The solidity and heft of the everyday world are, at bottom, trapped energy. The few quarks that do carry a little real weight get that weight from elsewhere, from their interaction with a field that fills all of space, a different mechanism entirely. But that small contribution barely matters for the proton. Strip it away, imagine the quarks as truly weightless, and the proton would still have almost all of its mass, because almost all of it was energy to begin with. The heaviness of matter does not need heavy ingredients. It needs only the fierce energy of the colour force, and that the proton has in abundance. This is one of the deepest truths the strong force teaches, and it sets up the final turn of the inner story. If the quarks inside ordinary matter weigh almost nothing, if they are nearly massless, then they have a hidden near symmetry, a balance that holds when mass is set to 0. That near symmetry, and the way nature quietly breaks it, is the secret origin of the pion itself. The pion is not merely built from a quark and an antiquark. It is born from the breaking of a symmetry in the nearly weightless world of the quarks, and understanding that is understanding the pion at its very root. We turn now to the symmetry, and to the strange way the emptiness of space chooses to break it. To reach the pion's deepest origin, we have to look at the quarks inside it when their tiny weight is set aside, treated as 0. The lightest quarks, the ones that make up protons, neutrons and pions, weigh almost nothing on the scale of the strong force. For understanding the pion, it is close to the truth, and far more revealing, to pretend they weigh exactly nothing, and then add their small real weight back at the end. In that nearly weightless world, the quarks have a hidden symmetry, and the symmetry has to do with a property called handedness. Every quark, like many particles, has a kind of built-in spin, and that spin can be lined up with the direction the quark moves or against it. A quark whose spin points along its motion is called right-handed, like a screw turning forward as it advances. A quark whose spin points against its motion is called left-handed, turning the other way. This handedness is a real and basic property. The names come from the way the fingers of your right or left hand curl when your thumb points along the direction of travel. Here is the symmetry. If the quarks were truly massless, their handedness would be fixed and separate. A left-handed quark would stay forever left-handed, a right-handed quark forever right-handed, and the two kinds would live in their own worlds, never mixing, each obeying the strong force on its own. The laws would treat left and right as two independent families that could be rotated and relabeled without changing any physics. This near symmetry between the handedness families is called chiral symmetry, from the Greek word for hand. In a world of massless quarks, it would be exact. Why does mass break it? Because a particle with weight can never move quite at the speed of light, and that opens a loophole. For anything slower than light, you could imagine racing ahead of it and looking back, and from that vantage its motion would appear reversed while its spin stayed put, flipping its apparent handedness. A massive quark therefore cannot keep its handedness pure. Left and right blur into each other. Only a truly massless particle locked at light speed keeps its handedness forever fixed. So mass is exactly what spoils the clean separation of left and right. Give the quarks even a little weight, and the chiral symmetry becomes only approximate. Since the lightest quarks weigh so very little, the chiral symmetry is very nearly exact in nature. It is a real near symmetry of the strong world, broken only slightly by the small quark masses. Physicists expected, as they always do with a near symmetry, that it would leave clear fingerprints on the particles, that the strong force would show signs of treating left and right as almost interchangeable. But when they looked, something was wrong, in a way that turned out to be profound. The symmetry was there in the underlying laws, the quarks nearly massless and left and right nearly separate. Yet the world of actual particles did not show the symmetry plainly. The protons and neutrons did not come in the neat mirror-paired families that an exact chiral symmetry would demand. The symmetry was present in the equations but absent from the things the equations described. It was as though a law of perfect balance were written into nature, and yet the world built from that law came out unbalanced. This mismatch is the doorway to the Pion's origin. A symmetry that lives in the laws but not in the world is not simply broken or absent. It is hidden in a precise and remarkable way, broken not by the laws themselves but by the state the world settles into. The emptiness of space, the vacuum, makes a choice, and that choice hides the symmetry and gives birth to the Pion. To see how, we have to look at what it means for a symmetry to break not in the law but in the void itself. A symmetry that is written in the laws but missing from the world is said to be spontaneously broken, and the idea is subtler and more beautiful than simple breaking. The laws keep their perfect balance. What loses the balance is the particular state the world happens to settle into, the lowest energy condition that nature actually occupies. The rules are symmetric, the resting place is not. There is a plain picture for this. Imagine a pencil balanced perfectly on its point. While it stands, it has no preferred direction. Every way around it is the same, fully symmetric. But that standing state is unstable, and the pencil must fall. When it falls one particular way, and now there is a special direction, the way it points on the table. The symmetry of all directions is gone, not because the laws of the pencil favoured any direction, but because the pencil had to settle somewhere, and settling meant choosing. The law stayed symmetric, the chosen state did not. The vacuum of our universe, the empty space that is the lowest energy state of everything, did something like this with chiral symmetry. The laws of the strong force treat left-handed and right-handed quarks as nearly interchangeable, but the vacuum, the resting state the universe fell into, does not respect that balance. Empty space is not truly empty. It is filled with a quiet sea of quark-antiquark pairs, constantly forming and merging, and this filling C pairs left-handed quarks with right-handed antiquarks throughout all of space. The vacuum itself links left and right everywhere, and that linkage is the pencil falling. The symmetry of the laws is hidden by the choice the emptiness made. When a symmetry breaks this way, in the vacuum rather than in the law, nature produces something specific and unavoidable. A particle. Not just any particle, but a very light one. A soft ripple in the broken symmetry. Because the laws are still symmetric, it costs almost no energy to disturb the chosen state gently, to nudge the alignment of the vacuum a little this way or that. Those gentle nudges travel as a wave, and a wave of disturbance in a field is a particle. Since the nudge costs so little energy, the particle is very light. If the symmetry were exactly perfect, the particle would weigh exactly nothing. That particle is the pion. The pion is the soft ripple of broken chiral symmetry, the wave you get when you gently disturb the aligned vacuum. This is the pion's deepest identity, far beneath being a quark and an antiquark, beneath being Yukawa's messenger. It is the sound the broken symmetry makes, the nearly weightless echo of the vacuum's choice. The three pions, positive, negative and neutral, are the three ways the vacuum's alignment can be nudged, three modes of the same soft ripple. This explains at last why the pion is so strangely light. It is the lightest meson by far, much lighter than its proper place among the quark combinations would suggest. Now the reason is clear. The pion is light because it is the ripple of a near-perfect symmetry, and the ripple of a perfect symmetry would be weightless. The pion has a small mass only because the symmetry is not quite perfect, only nearly so, spoiled by the small real weights of the quarks. The pion's lightness is the measure of how close the chiral symmetry comes to being exact. So the pion carries a memory inside it. Its small mass is a direct record of the tiny quark masses that keep the symmetry from being perfect. Make the quarks heavier, and the pion would grow heavier in step. Make them truly massless, and the pion would vanish into a weightless ripple. That precise link between the pion's mass and the quark's mass is not a vague idea but a sharp relation, written down in a single clean statement, and it is the next thread to follow. The link between the pion's mass and the quark's mass was made exact in 1968, in a relation worked out by Murray Gell-Mann together with two colleagues, Harold Oakes and Benjamin Renner. It is known by their three names, and while the full statement is mathematical, its meaning can be said plainly. The relation ties three things together: the small mass of the pion, the small masses of the lightest quarks, and the strength of the vacuum's filling C that broke the symmetry. Fix any two, and the third follows. What the relation says in words is that the pion's mass squared grows in step with the quark masses. Double the quark masses, and the pion's mass squared doubles. The pion does not simply inherit the quark mass directly, it inherits it through this squared relationship, which is why the pion can be so light even though it is the ripple of a symmetry broken by quark masses that are themselves not quite zero. The smallness of the quark masses is amplified into the particular smallness of the pion through this precise law. This relation is one of the loveliest results in the physics of the strong force, because it connects the visible to the hidden. The pion's mass is something you can measure directly. You make pions in an accelerator and weigh them. The quark masses and the strength of the vacuum C are hidden quantities, never seen directly, buried inside particles that can never be opened. The relation lets you reach the hidden from the visible. Measure the pion, and you have a handle on the quark masses and on the depth of the vacuum's filling, neither of which you could ever weigh on their own. It also confirms with precision the whole picture of the pion as the ripple of broken symmetry. If the pion were just an ordinary particle built from a quark and an antiquark, there would be no reason for its mass to track the quark masses in this exact squared way. The relation only makes sense if the pion is the soft echo of chiral symmetry, light precisely because that symmetry is nearly perfect. The clean fit between the relation and the measured pion mass is strong evidence that the strange story of the broken symmetry in the filled vacuum is true. There is a striking consequence hidden in the relation. It says that if the quark masses were exactly zero, the Pion's mass would be exactly zero too. A Pion built from truly massless quarks would itself be weightless, a perfect ripple costing no energy at all. The Pion's mass is, in this precise sense, borrowed entirely from the small masses of the quarks. Every bit of the Pion's weight traces back to the quarks not being quite massless. The Pion remembers the quark masses, and the relation is the exact form of that memory. This gives physicists a powerful tool. They can imagine turning the quark masses up or down, and the relation tells them exactly how the Pion would respond. In computer calculations of the strong force, where the quark masses can be set to any value the physicist chooses, this relation is a constant check. Set the quarks heavier, watch the Pion grow heavier by the square root rule, and confirm that the calculation is behaving as the deep theory says it must. The relation is both a window into the hidden and a measuring stick for the calculations that probe it. So the Pion's small mass is now fully understood, traced all the way down. It is light because it is the ripple of a near-perfect symmetry, and its exact small weight is set by the tiny quark masses through the relation of Gell-Mann, Oakes and Renner. But this picture leaned on something we passed over quickly, the filling sea in the vacuum, the quark-antiquark pairs that fill all of empty space and break the symmetry. That sea deserves a closer look, because it means the emptiness around you is not empty at all. The breaking of chiral symmetry rests on a strange claim that deserves to be faced directly. Empty space is not empty. The vacuum, the lowest energy state of the universe, the nothing that remains when you remove every particle and every scrap of light, is in fact filled. It is filled with a sea of quark-antiquark pairs, forming and dissolving everywhere, all the time throughout all of space. Physicists call this filling the quark condensate, and it is as real as anything in the strong force, even though it is made of the very absence of particles. The word condensate borrows from the way steam condenses into water, many separate things settling into one connected whole. In the vacuum, countless quark-antiquark pairs settle into a single coherent sea, a uniform background that fills the universe evenly. It has no particles you can point to, no specks moving through it. It is a steady condition of space itself, a property of the void. Every point in empty space, including the space in this room and the space inside your own body, holds this sea. You're soaking in it now, and have been your whole life without any sign. This condensate is what breaks the chiral symmetry. It pairs left-handed quarks with right-handed antiquarks all through space, and that pairing is the linkage of left and right that the symmetry forbade. The vacuum chose to fill itself this way because the filled state has lower energy than the empty one. Nature settles into the filled vacuum the way water runs downhill. The emptiness is filled because filling it costs less energy than leaving it bare. The strong force makes the void prefer to be full. And the Pion is our window into this filling. Recall that the Pion is the soft ripple of the broken symmetry. But the symmetry was broken by the condensate, so the Pion is, in effect, a ripple in the condensate itself, a gentle wave passing through the filled sea of the vacuum. When you make a Pion, you're setting the vacuum's filling sea trembling a little. The Pion's very existence is proof that the vacuum is filled, for a ripple needs something to ripple in. There could be no Pion in a truly empty void. This is why the Pion matters far beyond the nucleus. It is the most direct evidence we have that empty space has a rich structure, that the vacuum is a physical thing with properties, not a featureless nothing. Through the Pion, and through the Gell-Mann-Oakes-Renner relation that ties the Pion's mass to the strength of the condensate, physicists can actually measure a property of the void. They can put a number to how strongly the vacuum is filled, how dense the quark-antiquark sea is, by weighing the ripple that runs through it. The Pion lets us measure the emptiness. It is worth pausing on how strange and how settled this is. The idea that the vacuum is a living, filled medium can sound like wild speculation, but it is among the well-tested features of the strong force, confirmed by many measurements and by direct computer calculation of the vacuum structure. The emptiness around you genuinely holds a sea of quark-antiquark pairs, breaking a symmetry, giving the pion its lightness, and through that lightness shaping the nuclear force that holds you together. The void is not the absence of everything. It is a quiet, structured presence. With this, the inner story of the pion is complete, traced from a particle in the sky down to a ripple in the filled vacuum. Now the path turns back outward, to use this deep understanding to rebuild the nuclear force from the ground, more carefully and more truly than Yukawa could, starting from the pion as the ripple it truly is. Knowing the pion as the soft ripple of broken symmetry gave physicists something Yukawa never had: a principled way to rebuild the nuclear force from the ground up. The key step came from Steven Weinberg, one of the great theorists of the century, who in the late 1970s and through the 1990s realised that the pion's special nature could organise the whole messy problem of nuclear binding into a clean, ordered scheme. The approach is called Chiral effective field theory, and its power is that it knows what to include and in what order. The idea works because the pion is light and the energies inside a nucleus are low. When particles move slowly and gently, the strong interactions among them can be sorted by size, with the largest effects first and each later correction smaller than the last. The pion, being the lightest thing the strong force makes, dominates the long-range part of the force, exactly as Yukawa said. But now physicists could go further, adding the exchange of 2 pions at once, then 3, each a smaller correction, building the nuclear force as an ordered series of ever finer terms. This ordering is the heart of the method, and it rests directly on the pion being the ripple of a near-perfect symmetry. Because the symmetry is nearly exact, the pion interacts only weakly when its energy is low, and the strength of each successive term in the series can be estimated and controlled. The near symmetry that gives the pion its lightness also tames its interactions, making the whole series behave, with each layer a predictable step smaller than the one before. Yukawa's single pion exchange becomes just the first and largest term in a controlled expansion, with the deeper symmetry guaranteeing the rest can be added in order. What makes this more than bookkeeping is that it connects the nuclear force to the deepest theory. The terms in the series are built to respect chiral symmetry and its breaking, the same symmetry that governs the quarks and the vacuum. So the force between nucleons is no longer a separate made-up rule. It descends, in an orderly way, from the underlying theory of quarks and gluons, through the pion as the messenger that survives at long range. The leftover force is rebuilt as a controlled approximation to the real strong force, with the pion carrying the deepest physics out to the scale of the nucleus. The method delivered real results. Physicists used it to compute the force between 2 nucleons to high precision, then between 3, capturing details that older, more guessed-at forces had missed. The forces that come out of this scheme are now among the most accurate descriptions of how nucleons interact, used to calculate the properties of light nuclei from first principles, with the pion's exchanges at every level. The patient, ordered building from the pion outward works. There is a quiet vindication in this for Yukawa. He guessed that a single exchange pion was the nuclear force. He was right about the largest piece, the long-range tail, the part that reaches farthest between nucleons. What he could not know was that his single pion was the first term of a deep and orderly series, grounded in a symmetry no one had yet discovered, descending from quarks he had never imagined. His guess was the leading edge of something far richer, and the richness only confirmed how well he had seen the essential thing. But the ordered series held a surprise that Yukawa's simple picture could never have contained. When physicists added the next terms, they found forces that act not between pairs of nucleons but among 3 at once, a kind of binding that no pairing of 2 could ever produce. The pion, it turned out, does not only pass between 2 nucleons, it can weave among 3, and that 3-way whisper is the next thread. In Yukawa's original picture, the nuclear force was a thing between 2 nucleons, a pion passing from one to another. Add a third nucleon, and you simply had 3 separate pairs, each trading pions, the total force being the sum of the pairings. For a long time this seemed enough, But when physicists built the nuclear force carefully from the Pion outward, in Weinberg's ordered scheme, they found that it was not enough. There is a force that acts on 3 nucleons at once, all together, that cannot be broken down into separate pairs. The Pion makes it possible. Picture how it happens. 1 nucleon emits a pion. But instead of that pion travelling straight to a second nucleon and being absorbed, it is intercepted along the way by a third nucleon that scatters it, redirects it, and only then does it carry on to its destination. 3 nucleons are involved in a single linked event. The one that sent the pion, the one that deflected it in passing, and the one that finally caught it. The result is a force whose strength depends on all 3 nucleons together, on their arrangement as a trio in a way no sum of pairs can reproduce. This is the 3-body force, and it is genuinely a whisper, much fainter than the main pairwise force. For 2 nucleons, the force is loud and direct. The 3-body force is a smaller correction, a subtle extra binding that appears only when 3 nucleons are close together at once. In Weinberg's ordered series, it shows up naturally as one of the finer terms, predicted to exist and predicted to be small, with its size set by the same symmetry that governs everything else. The scheme did not just allow it, it told physicists roughly how strong it should be. Faint as it is, the 3-body force matters. There are properties of nuclei that the pairwise force alone gets wrong, that only come right when the 3-body whisper is added in. The exact way certain nuclei are bound, the fine details of their structure, the behaviour of nuclei rich in neutrons, all depend on this small 3-way force. Leave it out, and the calculations miss. Put it in, and they fall into agreement with what experiments measure. The whisper is quiet, but in the careful accounting of nuclear structure, it is the difference between right and wrong. There is something striking in this. The Pion, already revealed as Yukawa's messenger, then as a quark pair, then as the ripple of the broken vacuum, now shows yet another face. It can bind 3 things at once through a single shared exchange, weaving a force that has no meaning for any pair alone. The nucleus is not merely a collection of pairwise grips. It is a web in which 3 nucleons can be bound together by a pion passing among them, a subtlety invisible in Yukawa's first sketch, but flowing naturally from the deeper theory built on the Pion's true nature. This 3-body force is an area of active work, not a closed book. Physicists are still pinning down its exact strength, still tracing how it shapes the most delicate nuclei, still folding it into the great calculations that build nuclei from first principles. It stands as one of the clearest signs that the modern picture of the nuclear force, built carefully from the Pion, captures things the old picture could not. The Pion binds not only in 2s but in 3s, and perhaps more faintly still in greater numbers yet. And yet, for all the success of this Pion-built picture, there is an honest puzzle waiting in the data, a place where the pions that should be inside nuclei seem strangely hard to find. That puzzle is the next thread, and it keeps the wonder honest. For all the triumph of the Pion picture, there is a place where it runs into trouble, and honesty requires facing it. If nucleons are bound by exchanging pions, then a nucleus should be, in a sense, full of pions, a cloud of them constantly in flight between the nucleons, carrying the force. Those pions should carry a share of the nucleus's energy and momentum, and there should be experimental signs of them, extra pions worth of stuff inside a nucleus compared to the same nucleons taken alone. Physicists went looking for those nuclear pions directly, and the search did not go as expected. The story begins with a surprise found in 1983 by a group called the European Muon Collaboration, a result now known by their initials as the EMC effect. They fired high-energy beams into nuclei to probe the quarks inside, comparing the quarks in a nucleon bound in a heavy nucleus to the quarks in a free nucleon. By the simplest expectations, binding a nucleon into a nucleus should barely touch its quarks. The binding force is feeble compared to the fierce energies that hold the quarks themselves. The quarks inside a bound proton should look almost exactly like the quarks inside a free one. They did not. The quarks inside a bound nucleon were measurably different, shifted in how they shared the nucleon's momentum, as though the nucleus reached inside each nucleon and altered its very quark structure. This was a shock. The gentle force binding nucleons together seemed to be disturbing the deep, strong interior of each nucleon, which it had no business doing. The effect was clear, repeated and unexplained, and decades later it is still not fully understood. It remains one of the honest open puzzles of nuclear physics. The Pion enters because one natural idea for explaining the EMC effect was the cloud of exchanged pions. If a nucleus carries extra pions flying between its nucleons, those pions carry quarks and antiquarks of their own, and they might account for the altered quark picture. So physicists made a sharp prediction. A nucleus should contain a measurable excess of pions, a detectable surplus of them over the bare nucleons, and that surplus should show up in experiments that count the antiquarks inside nuclei. It was a clean test of the idea that the nucleus is full of exchange pions. The test was carried out, and the predicted excess of pions was not found. Experiments that should have seen the surplus of nuclear pions came up short. The extra antiquarks that a sea of exchange pions would bring were simply not there in the amount expected. The pions that the binding picture seemed to demand did not show themselves in the data. This is the puzzle of the missing pions, and it sits in genuine tension with the simple notion of a nucleus stuffed with exchange pions carrying the force. How can both things be true, that pions bind the nucleus, and that the nucleus shows no surplus of pions? The resolution is subtle and still debated. The pions of the modern theory are deeply virtual, borrowed and repaid, never quite real particles with their own lasting share of momentum, and the careful accounting of how they contribute is more delicate than the naive picture suggested. The force is built from pion exchange, yet the nucleus need not look like a bag of extra pions. Holding both truths at once, the binding role and the missing surplus, is part of the unfinished work. This is the wonder kept honest. The Pion picture is powerful and largely right, and it still has corners where the data resist it, and physicists do not yet fully agree. The missing pions are a reminder that the nucleus is not a solved thing, and there are places where the Pion story turns stranger still, out in the crushing matter of a dying star, where pions might do something they never do on Earth. Carry the Pion now into one of the most extreme places in the universe, the heart of a neutron star. When a massive star burns out and collapses, its core can be crushed so hard that protons and electrons are jammed together into neutrons, and a vast ball of nearly pure neutron matter remains, a city-sized sphere as heavy as the sun. Inside it, matter is squeezed denser than anything else in the cosmos short of a black hole, denser even than the matter inside an ordinary nucleus. In that crushing density, the Pion may do something it never does in ordinary matter. On Earth, a Pion is fleeting. It must be made in a violent collision, and it decays almost at once. It costs energy to bring a Pion into being, the energy of its mass, and matter does not produce pions freely because that cost is too high. But inside a neutron star, the situation can change. The neutrons are packed so tightly and pressed so hard that it may become energetically favourable for the matter to fill itself with pions, to grow a steady, permanent population of them woven through the neutron sea. The pions would no longer be fleeting messengers, but a standing feature of the matter itself. This possibility is called Pion condensation, and it echoes the condensate in the vacuum, though it is a different thing. In the vacuum, the condensate is quark-antiquark pairs filling empty space. In a neutron star, a Pion condensate would be a sea of pions filling the dense matter, a coherent population of them settling into the lowest energy state of the crushed material. The matter would in effect decide that holding a sea of pions costs less energy than not holding them, and so the pions would appear and stay, a new phase of matter found only under that extreme squeezing. If it happens, it would change the neutron star profoundly. A Pion condensate would soften the matter, making it easier to compress, which would alter how massive a neutron star can grow before collapsing into a black hole. It would also open new ways for the star to shed energy, letting it cool faster than plain neutron matter would. These are not idle details. They connect to things astronomers can actually observe: the masses of neutron stars measured by their pull on companions, and their temperatures, read from the light they emit as they age. The Pion's behaviour in the deep interior could leave fingerprints visible across the galaxy, but whether Pion condensation truly happens remains an open question, and an honestly hard one. The matter inside a neutron star is so dense that the strong force there is in a regime physicists cannot fully calculate. The same difficulty that locks quarks inside nucleons makes the dense interior resist clean computation. Whether the pions actually condense, at what density it would begin, and how much it would change the star, are all matters of active research and real uncertainty. Some calculations favour it, others suggest competing effects step in first. The answer is not settled. What is clear is that the Pion's reach extends from the smallest nucleus to the densest stars. The same particle that binds a deuteron, that ripples in the vacuum, that whispers among three nucleons, might also fill the core of a dead star and shape its fate. The Pion is not only a piece of the atom's centre. It is a thread running through matter at every scale, from the laboratory to the collapsed remnants of stars, carrying the strong force into the most extreme corners of the universe. And there is one more turn in the Pion's story, a strange one, where physicists found that sometimes the cleanest way to understand a nucleus is to leave the Pion out entirely. Here is a turn that seems to undo everything. After building the nuclear force so carefully from the Pion, physicists found that for certain problems, the best approach is to throw the Pion away. They developed a version of nuclear theory with no pions in it at all, called pionless theory, and for a particular class of systems it works beautifully. To see why, you have to remember where the Pion lives in the force, at long range, reaching the farthest of any part of the strong interaction between nucleons. Long range is a relative thing. The Pion's reach, set by its mass, is short compared to an atom but long compared to the very closest approaches of two nucleons. Now consider a system where the nucleons are bound so loosely that they spend most of their time far apart, farther even than the Pion's reach. The deuteron is nearly like this, barely bound, its proton and neutron lingering at the edge of the force. For such loosely bound systems, the nucleons are mostly outside the range where the Pion matters. The Pion's exchange happens too close in to be the main story. In that case, you can drop the Pion entirely and describe the force as if it acted only at a single point, a contact between nucleons that touch, with nothing reaching between them at a distance. This sounds crude, but for very loosely bound systems it captures the essential physics, because those systems barely feel the detailed shape of the force at all. They are so spread out, so weakly held, that only the gross strength of the force matters, not whether a Pion or anything else carries it. The pionless theory keeps just that gross strength and discards the rest. What emerges from this is one of the strangest and most beautiful results in the field, a kind of universality. Systems that are loosely bound in this way behave almost identically, regardless of what they are made of, regardless of the details of the force binding them. A pair of nucleons barely bound, certain atoms barely bound to each other, cold atoms tuned in a laboratory to cling weakly, all show the same patterns, the same relationships among their properties. The deep details wash out, and a simple shared behaviour remains. Loosely bound things forget what they are made of and obey a common set of rules. This universality reaches a remarkable peak in a result about three bodies, found by the physicist Vitaly Efimov in 1970. He showed that three particles, each pair barely failing to bind, can nonetheless bind in threes, and not just once, but in an infinite tower of ever larger, ever fainter bound states, each a scaled copy of the one below it, marching off towards zero. This Efimov effect is a pure consequence of loose binding and three bodies, owing nothing to the specific force involved, and after decades as a prediction, it was finally seen in ultra-cold atoms in 2006. The same physics that lives in loosely bound nuclei appears in clouds of trapped atoms. so the pion's absence teaches as much as its presence. When nucleons are held tightly enough to feel the pion's reach, the pion is essential, and the careful chiral theory is the right tool. When they are held so loosely that they drift beyond the pion's range, the pion becomes irrelevant, and a pionless theory reveals a universal behaviour shared across all of weakly bound matter. Knowing when the pion matters and when it does not is itself a deep piece of understanding. The pion's reach defines the boundary between two different worlds of physics. To pin down all of this, the role of the pion and its absence, the forces among 2 and 3 nucleons, the structure of the vacuum itself, physicists turn to a tool that tries to compute the strong force directly, from its deepest equations, with no approximations at all. That tool is the next thread. There is a way to study the strong force that sidesteps every approximation, every clever scheme, and goes straight to the fundamental equations of quarks and gluons. It is to solve those equations directly by brute computational force on the largest computers in the world. This approach is called lattice quantum chromodynamics, lattice QCD for short, and it is the closest thing physicists have to growing nuclei and pions from first principles, with nothing put in by hand. The difficulty the lattice overcomes is the one that has haunted this whole story. The strong force is too strong to handle with the usual tricks. For weaker forces, physicists calculate by treating the interaction as a small disturbance and adding up corrections, each smaller than the last. The strong force, at the scale of nucleons, is too fierce for that. The corrections do not shrink, and the method fails. The quarks are locked together too tightly to be teased apart on paper. Some other way was needed, one that did not lean on the force being weak. The lattice provides it by a bold move. It replaces smooth, continuous space and time with a grid, a lattice of points, like the corners of a vast three-dimensional checkerboard extended through time. The quarks live on the points of the grid. The gluons live on the links between them. With space and time chopped into this finite grid, the equations of the strong force become a huge but finite calculation, something a computer can grind through directly, summing over the countless possible arrangements of quarks and gluons to find what the strong force actually does. No approximation of weakness is needed. The full force is computed as it is. The cost is staggering. The grid must be fine enough to capture the small distances inside a nucleon and large enough to hold a whole nucleus, and the number of arrangements to sum over is beyond astronomical. These calculations run for months on the most powerful supercomputers built, consuming the kind of resources usually reserved for modelling climates or designing aircraft. Growing even a single pion or a small nucleus from the raw equations is a feat at the very edge of what computation can do. The lattice is a slow machine, patient and enormous, grinding the deepest equations into concrete numbers, and it works. Lattice QCD has computed the mass of the proton from first principles, starting from nothing but the quarks and gluons and their interactions, and the answer comes out right, matching the measured proton mass. This is a profound confirmation. The heaviness of ordinary matter, shown earlier to be mostly trapped energy, can be calculated from the bare theory and agrees with reality. The lattice has grown the pion too, and confirmed the Gell-Mann-Renner relation by computing how the pion's mass changes as the quark masses are dialed up and down, exactly tracking the square root rule. The lattice is now reaching further, toward computing the forces between nucleons directly, growing the nuclear force itself out of quarks and gluons rather than building it from the pion by hand. This is enormously hard at the frontier of the field, and only the simplest cases have begun to yield. But the direction is clear. In time, the lattice may grow whole nuclei from first principles, with the pion emerging on its own as the long-range messenger, no longer assumed but derived, the leftover force appearing naturally from the deeper one. The machine that computes the vacuum may yet show the entire story assembling itself from the bottom. With the lattice, the long arc of understanding closes a loop. The strong force, first glimpsed as a mystery holding the nucleus together, can now be computed from its deepest equations and made to reproduce the world. It is time to gather the whole thread, from the stone in your hand to the living vacuum, and see the single story it tells. Step back now and see the whole thread pulled tight, because a great deal has changed since the stone in your hand. The question was simple: what holds the centre of an atom together? The answer turned out to open one door after another, each leading deeper, until the nature of matter itself looked different than it had at the start. Gather the through line, and three great surprises stand out, each overturning something that seemed obvious. The first surprise is that the force binding the nucleus is not fundamental. It feels like the strongest, most basic thing in nature, the grip that overpowers electricity and holds matter together. But it is a leftover, a faint residue of a deeper force, the colour force between quarks, leaking just past the surface of each colour-neutral nucleon. The nucleus is held by the crumbs of a fiercer force raging inside its pieces, the same way neutral atoms cling by the crumbs of electricity. The grip you feel pressing the stone into your palm is a shadow of a stronger grip you can never see directly, one layer down. The second surprise is where the weight comes from. The heaviness of the stone, of your body, of nearly all ordinary matter, is not the weight of solid stuff packed inside. It is energy, the bottled energy of quarks racing and gluons binding within each proton and neutron, given heaviness by the equivalence of energy and mass. The quarks themselves weigh almost nothing. Mass is mostly motion and binding. The solidity of the world is trapped energy wearing the appearance of substance, and when you lift something heavy, you are lifting, almost entirely, the caged fury of the strong force. The third surprise is that empty space is not empty. The vacuum is filled with a sea of quark-antiquark pairs, the condensate, which breaks a deep symmetry of the quarks and chooses a direction the laws themselves do not prefer. And the Pion is the ripple of that broken symmetry, the soft wave running through the filled vacuum, light precisely because the symmetry it rides on is so nearly perfect. The Pion is our window into the living emptiness, the proof that the void around you has structure, and the tool by which its filling can be measured. These three surprises are one story, and the Pion ties them together. It is the leftover force made visible, the long-range messenger of the residual colour force. It is born from the same energy that gives matter its weight, built from quarks whose mass is almost nothing, and it is the ripple of the broken vacuum, carrying the deepest symmetry of the strong force out to the scale of the nucleus. Yukawa imagined a single particle to explain why the nucleus holds, and that particle turned out to be a thread running through every layer, from the binding of a deuteron to the structure of empty space. The story is not finished, and that is part of its honesty. The missing pions of the EMC puzzle still resist a full explanation. Whether pions condense in the hearts of neutron stars is unknown. The three-body force is still being pinned down, and the lattice is still learning to grow nuclei from the bare equations. The Pion has been understood far more deeply than Yukawa could have dreamed, and it still holds open questions that working physicists chase today. The wonder is real because the understanding is real, and the edges where it runs out are real too. What remains is to bring all of this back to where it began, to the stone, to your own hand pressed flat against the table, and to feel what that simple solid push really is now that we have followed it all the way down. The last step is the shortest distance and the longest journey, from the deep vacuum back to your fingertips. Press your hand flat against the table again and feel it push back. At the start, that solidity was the simplest fact in the world, a plain pushing of solid against solid. Now follow what is truly happening under your palm, all the way down, and the simple push opens into the whole story we have travelled. Your hand does not touch the table, not really. The atoms in your skin never meet the atoms in the wood. What stops your hand is the electric repulsion between the electron clouds of your atoms and the electron clouds of the table's atoms, two haze-like shells of charge refusing to overlap. The solidity you feel is that refusal, a force held across a tiny gap that never closes. You have spent your whole life never once touching anything, held always a hair's breadth away by the push of charge against charge. But go to the weight behind that push, the heaviness of your hand and the table both, and you reach the strong force and the pion. Nearly all that weight is the energy bottled inside the protons and neutrons, the racing of quarks and the straining of gluons, made heavy by the equivalence of energy and mass. The protons and neutrons themselves are held into nuclei by the residue of the colour force, carried at its longest reach by the pion, the ripple of the broken vacuum. The heaviness pressing your hand toward the table is, almost entirely, the caged energy of the strong force, with the pion woven through it as the messenger that keeps the centres of your atoms from flying apart. So what holds the centre of an atom together? The simplest true answer is this: a leftover of the deepest force in nature, the colour force between quarks, carried between protons and neutrons by the pion, the lightest echo of a symmetry broken in the emptiness of space. That is the grip that has held the iron in a stone steady since it was forged in a dying star, the grip that holds the atoms of your own body together as you sit and read. It has never once failed in you. If it did, you would not come apart slowly. You would simply cease, in a flash, your nuclei unbinding all at once. Widen out now, one last time. The same pion that binds your atoms binds the atoms of the table, the earth, the sun, every star you have ever seen. The same living vacuum fills the space inside you and the space between galaxies, the same condensate, the same broken symmetry, the same soft ripple. The carbon in your hand and the oxygen in your breath were assembled in stars by this force, their nuclei built grip by grip, pion by pion, in the cores of suns that died before the earth was born. You're held together by the leftover of a force you cannot see, made of weight that is mostly motion, soaking in an emptiness that is quietly full. The stone was never simple. Your hand on the table was never simple. Behind the plainest solidity in the world stands the strong force, the pion, the quarks, and the living vacuum, the whole hidden architecture that lets matter hold its shape at all. The wonder was there the entire time, in the most ordinary thing you could do, pressing your hand against a surface and feeling it hold. Now you know, a little, what is doing the holding. Sit with that the next time something solid pushes back. It is the deepest physics in the universe, quietly keeping the world together and keeping you together too.